Welcome to OPStudio by OpenPhase Solutions. In this tutorial, we will simulate a tensile test of a polycrystalline aluminum sample using crystal plasticity. We'll go step by step from setting up the model to running the simulation and visualizing the results without writing any custom code. The goal is simple. We want to connect what we measure at the macro scale with what actually happens inside the material at the grain level. In a real tensile test, a metal sample is pulled under load. The force and displacement we measure are not coming from a single structure, but from millions of grains deforming together. Each grain has its own crystallographic orientation. Because of this, every grain responds differently to the same load. This is where OPStudio becomes powerful. Instead of assuming the material is uniform, we directly simulate the polycrystalline microstructure. Now we apply a strain-controlled tensile load. As the material is stretched, stress develops inside the structure, but the stress is not uniform. Some grains carry more load, while others yield earlier. This creates a heterogeneous stress field inside the material, and this is exactly what crystal plasticity captures. It resolves deformation at the grain scale and connects it to the overall response. Now that we understand the concept, let's look at the model. We use crystal plasticity to describe deformation inside each grain. Plastic deformation occurs through slip-on-slip systems, defined by slip directions and slip planes. Because each grain has a different orientation, these systems respond differently to the applied load. Using Schmidts' law or the Schmidt tensor, we calculate the resolved shear stress on each slip system. When the resolved shear stress reaches the critical value called critical resolved shear stress, the slip system becomes active. The slip rate then increases with stress, showing rate-dependent behavior. As deformation continues, the material hardens due to interaction between slip systems. In this way, we capture how individual grains deform and how their combined behavior gives the overall mechanical response. For this tutorial, use a predefined workflow and select Choose Preset. In the Preset selection menu, OPStudio provides several predefined simulation templates. For this tutorial, select the polycrystal tensile test, which is configured specifically for doing tensile tests on polycrystal material. You can also see the documentation of this predefined template. To do that, select View Details. All the information is provided here, including the simulation workflow. The input parameters used in this study are also provided. You can get the mechanical load information from here. At the end, the output from the simulation is also provided. Once you've reviewed the information, close the window. Afterward, click Finish to go to the Phase Setup tab. In the Phase Setup step, the aluminum element and FCC-L12 phase is already selected. We'll keep these unchanged for this simulation and proceed by clicking Apply and Continue. In the left panel, all the active modules for the simulation are displayed. First, focus on the Runtime Control tab. Here, you'll see the total number of time steps, which is set to 5,000. The simulation output is written to disk as VTK files every 100 time steps, and the screen output is also updated every 100 time steps, allowing you to monitor the simulation's progress. The time step size, denoted as dt, is set to 1 times 10 to the power of minus 3, and the simulation is configured to run on 4 OpenMP threads. In the Boundary Conditions section, periodic boundary conditions are applied for the microstructure. Moving on to the Grid Parameters section, the interface width of the diffuse interface is set to 4.5. The grid spacing is set to 1 micrometer, and the system size in the two-dimensional grid is 100 grid cells in both the X direction and the Z direction. Additionally, 1 boundary cell is applied in each dimension, which has already been set by the preset. The interface energy is selected as 0.05 joules per meter squared, with the interface mobility set to 1 times 10 to the power of minus 17, which is very low and frees the microstructure. Finally, the tensile test takes place at room temperature, so a temperature of 300 Kelvin is selected. In the Crystal Plasticity panel, a file from the predefined preset folder is already selected. Copy the file path, open the file browser, and paste the path. Here, the preset file named Polycrystal OPIP file is available. This file contains all the parameters used for the crystal plasticity model. Here, the phenomenological model is selected, and the slip mode is enabled for the crystal plasticity calculations. Multiple slip systems are available, and the complete list is shown here. Since aluminum is used in this simulation, the face-centered cubic slip system is selected. Hardening is also enabled, so the value is set to yes. The rate sensitivity exponent is selected as 10, and the slip rate is selected as 0.01. The hardening exponent is selected as 0.8. The initial critical resolved shear stress is selected as 100 megapascal, and the saturated critical resolved shear stress is selected as 300 megapascal. The initial hardening parameter is selected as 2 gigapascal, and the latent hardening parameter is selected as 0.3. The next value represents the maximum allowed shear increment, which depends on the maximum shear rate and the time step dt. If the calculated simulation value becomes larger than this maximum allowed shear stress, adaptive time stepping is automatically activated. In the Elasticity tab, multiple strain modes are available. For this simulation, the green Lagrange strain mode is selected. The elastic coefficient values are selected for the sample alloy, and the transformation stretches are set to unity. In the mechanical load section, boundary conditions can be applied. Here, a strain rate boundary condition is applied in the x direction, labeled as BCX with a strain rate value of 0.01. Now click Apply and Continue. It will take you to the Microstructure Selection tab. Here, a Voronoi microstructure with 20 grains is selected, and random crystallographic orientations are applied to the grains. Now click Apply and Continue. Now start the simulation. This will open the saving dialog. Here, the simulation settings can be saved, and the result files will also be created in the same folder. During the simulation, output is generated after every 100 time steps. To visualize the graphs, click on Update Data, then click the Stress Strain tab. Here, the stress values in each direction can be seen. For visualizing the results, open ParaView. Navigate to the directory where the simulation setting file was saved. Then open the VTK folder, followed by the phase fields file. Click Apply. From the drop-down menu, select Phase Fields. The displayed result is the microstructure generated using Voronoi tessellation, consisting of 20 grains with random crystallographic orientations. Next, open the Stresses file. From the drop-down menu, select Stresses in the X direction and then click Play. This will show the evolution of stresses during the simulation. Similarly, open the Plasticity settings file, select Plastic Strain in the X direction, and click Play to observe the evolution of plastic strain. These are the final visualization results of the simulation. If OPStudio fits your workflow, download the free trial or explore the licensing options on our website. Subscribe to our YouTube channel for more technical tutorials. Thank you for watching.